Hi everyone, welcome to class for week 3 of our falling mass rotating pulley lab. So today I just wanted to talk about a couple of things. I want to recap a little bit the theory. I want to go over the linearization of the model, of the idealized model, so that we're all on the same page. I want to say a little bit more about the data analysis. You've had the chance to think about some of the initial data we got last week, but I want everybody to be on the same page here, so I'll talk through some things. A quick side note about rotational inertia, and then part 2 of this video, today's video, will give you some tips for using Excel for your analysis. So to remind everyone, right, this is our idealized model for our falling mass rotating pulley for the acceleration of our falling mass, right? And so here, right, I is the rotational inertia of our pulley, and then m is our hanging mass, r is the radius of our pulley. Right, to linearize this model, right, what we want to do is the following, right? We can't change the moment of inertia of our pulley if we only have one. We can't change the pulley's radius either. The one thing that we can control here in order to test this model is the hanging mass, right? So we want to get something where we look at how some quantity associated with this acceleration changes as we change the mass. At varying. So you can think about ways to do that, but I think the best way here is to simply start by taking the reciprocal of both sides of this. Right. Nothing here is going to be 0, so that gives us 1 over a equals 1 plus I over mr squared divided by g, or if I write this in a more suggestive way, right, I now have 1 over a equal, I have 1 over g here, and then I simply have to, I also have to divide this term by g, right, and that gives me I over mg r squared, or right now what we can see, right, is that it's not linear in m, but it is linear in 1 over m. So let me write it explicitly in that form. So that gives me a 1 over a equals 1 over g plus, and I'll write this as in parentheses, I over g r squared times 1 over m, right? So here is our linearized model, and the things that I want to highlight, right, we want to look at 1 over a, right, and then 1 over g is our intercept. And then I over gr squared is our slope. So what we want to do then, right, is to plot in the following way. We want to plot 1 over my acceleration as a function of 1 over the mass. So hopefully we get a few data points, right, and right, when we assess whether or not a linear model is valid, right, we want to check for linearity, we want to check the slope, and we want to check the intercept. So if I just plot a couple of points here, hopefully what we see is something like this, right, where we have our intercept here, that's, hopefully we see that's 1 over g, and our slope is I over g r squared. Now we certainly know what we expect 1 over g to be, right? we can also go and measure the radius of our pulley. I'll do that carefully for our lab video on Thursday using a set of calipers. The trickier thing is to try to get an estimate of what the rotational inertia of our pulley is. Now that, I have some ideas, and I'll say something about what I means and how we can put some order of magnitude bounds on it at the end of this clip. So the first analysis task that I want to talk about to make sure we're all on the same page is the following: finding the acceleration and its uncertainty for one value of the hanging mass, right? So, right, just to remind you, right, the process is going to go like this, right? We know we have the counts for the rotating pulley, right? We have the count for that's related to the time it takes the pulley to turn 1/3 of a rotation, right? So we know the counts, right? And that leads to a time interval, right, for that 1/3 of a rotation. If we sort of make the assumption that we have some sort of average angular velocity during that time interval, right? If we know the rotation angle, which is 1/3 of a rotation, or 2 pi over 3 radians, right? We can then get an angular velocity omega out of that. Right? Once we have angular velocity, it's not hard to get omega squared, right? The other thing is we need the angle, right? And this is now the angle theta since the beginning, right? So we know that we're going to get a data point every 2/3 of a rotation. So we got our first data point at 0, 4 pi over 3 radians, 8 pi over 3 radians, etc. So we sort of combine these two things, omega squared, right? And what we want to do is to graph omega squared as a function of angle. Okay. Oops, other way around. As a function of angle, and right, and that ought to look something like that. Perhaps where I have, right, my omega squared equals my initial omega plus 2 alpha, let's call it theta, rather than it's really a delta theta, but if we started it at 0, let's just call it theta, right? And then, right, so our slope, right, gives us twice our angular acceleration. And then the key is to use our no-slip constraint. Right, A is alpha r, where r is the radius of our pulley, which, as I said, we'll measure tomorrow. So all of this you can do in a spreadsheet, right? Right. So, and you can organize your data in columns. So you might have a column for your counts. You might have another column for your time interval, delta t, your omega, right? You might get your angle, so your theta. You might do that as an increasing series, and then you're gonna have a column for your omega squared, and then if you have all of these columns, you can then construct a graph like that, and then get the slope. So I'll show you some of that in the Excel bit in the second part of today's class video. So let me just say one thing. So you can get the slope and uncertainty in the slope, and hence A and its uncertainty via the linest function. So as I'll talk about in the Excel video, the linest or linear estimation function gives you some statistical uncertainty on the fit parameters, namely the slope and the intercept. These statistical uncertainties have to do with the deviation between your model, so your straight line model, and your data points. Now, that's a valid thing to work with if it is the case that those individual data points have a small uncertainty. I think you'll be able to convince yourself that for our count data and our angle data, those uncertainties are in fact small, and that any uncertainty in the slope should in fact be dominated by the sort of statistical best fit issues. That is not a good way to think about things when there are significant uncertainties in the data points themselves. And I'll say more about that in a second when I talk about the next bit of the analysis. So the goal of the second part of our analysis is to test our linearized model like I talked about. You're going to want to do this right by determining the acceleration for several different masses. My suggestion, right, is to put each m in a different sheet, so in a different tab in the spreadsheet. And then this analysis, so this part B analysis in its own sheet. So again, here, right, what we as we said, right, we have our model ends up being 1 over A goes like 1 over G plus, right, I over G R squared times 1 over my mass. So as we said before, I want to plot 1 over A versus 1 over M, right? So, okay, so well, this time we'll want to do this with error bars. Plot 1 over A versus 1 over M with there will definitely be some uncertainty in the acceleration, and as we'll think about more later this week, there'll definitely be an uncertainty in the mass as well. So this is important. So let me try to sort of draw a graph of this, right? We should have some error bars, right? Because we have error bars, right, this time, right, you can't use the linest statistics to get the uncertainty in the slope and intercept. Linest can give you the best value, but you'll need to get the uncertainties by hand. So namely, calculate sort of a linear model as a function of just a slope and an intercept, play around with those numbers like you would if you were were fitting a graph on paper. And as we talked about, right, the slope and the intercept will allow you to determine G and with its uncertainty and the moment of inertia or rotational inertia, I with its uncertainty. So again, right, organize your spreadsheet into sensible columns, right? So you probably want, right, so each row will be a different mass. You probably want something like the mass, right, the uncertainty in the mass, the acceleration, the uncertainty in the acceleration, right, then your 1 over mass, the uncertainty in 1 over mass, right, and then the same thing for the 1 over the acceleration with its uncertainty. So the last thing that I want to just remind everybody of, we didn't really talk about this in detail in 117, so this isn't really a reminder, is just a little bit more about the moment of inertia, or rotational inertia, and how we can think about it. Because we're going to get that from our analysis, we want to have a way to think about what the value might be. So the general definition of rotational inertia is the following. This is hopefully sort of language that's a little familiar from 118. And it's the idea that, right, if I have some continuous object with some rotation axis, which I've sort of drawn as a little x here, I can think about that continuous object by imagining that I subdivide it into little chunks. So if I draw a little chunk here in purple, right? This little chunk, I can say it has a portion of the mass of my entire object, and I'll call the mass of that little chunk delta m. And then I can also define sort of a radial distance r, so a perpendicular distance here, between my little chunk of mass and my rotation axis. You did learn in 117 that for an object that is made up of discrete masses, right, I goes like the sum over all of the elements in the object, so of the sum delta m r squared, right? So I take the mass of every little chunk, I multiply by r squared, and add up over the entire object. From 118, hopefully it's not a huge surprise that for a truly continuous object, I just need to sort of take the limit of this as I make all my elements smaller and smaller. Right. And it should be no surprise that this means that my discrete summation turns into an integral. And I'll write it in a way that's more suggestive, so it's going to be the integral specifically of r squared dm. I'll write the differential last to make that more sort of closer to calculus notation. So this integral is sort of only nicely doable in special cases, but it does tell you, right, that what I says, right? I says that the further away from my rotation axis my mass is distributed, the larger my I is. So as if you do some calculus, right, you can show that if I have like a hoop of mass m and radius r, that should be a circle, right? If I have just a thin hoop here, right, where that's completely empty in the middle, all the mass, all of it is at radius r, and then it turns out that the rotational inertia is just the total mass m r squared. The other special case you want to think about is a disk, right? That's solid, and you can show with some calculus that for this, I is 1/2 the total mass times r squared. So, right, notice the dimensionality is the same, it's just the prefactor in front, 1 for a hoop, and 1/2 for a disc. Now our pulley, I would imagine, is somewhere in between these two, right? For our pulley, right, it's sort of solid with these holes in it, and I'm sort of failing at filling this in, but I think you get the picture. Right, so it's not like this case where all the mass is at the edges, but it's also not like this case where all the mass is sort of uniformly distributed throughout the entire round part. Right, so here I would expect I to be some constant times the total mass of the pulley times r squared, with my constant varying somewhere between these two limiting cases. So I would expect it to be somewhere between 1 and 1/2. There are some tricks you can think about for maybe estimating this constant in a more quantitative way. But there's, I think, enough uncertainty in everything else that that's not going to be super important, right? Because we can measure the radius of our pulley for sure. The mass is harder. I can think of some ways to get an order of magnitude estimate for the mass of our pulley. I don't think I can completely break the pulley apart, so I can just measure the mass of the wheel itself. If anybody has ideas, I'm all ears. But I think we'll be able to get an order of magnitude estimate of this mass, given the uncertainty there. Sort of having a sort of a factor of 2 uncertainty in this constant is, I think, not going to be a big deal. Either way, we should be able to get at least some order of magnitude estimate for the eye of the pulley, so that we can see whether what we get from our linearized model is plausible. So to wrap up today, we'll just take a look at, go to my computer and I'll show you some things in Excel.